let's see. Today we're just going to practice NMR problems. I know that this is a source of stress and anxiety because this is all new. Understand that the problems that I give you on the exam will all be solvable. And understand that NMR in some ways is like nomenclature. In the sense that you can always think of a more dastardly situation that you would be unable to deal with, and that's okay. You're going to have to trust me that I'm going to only give you problems that you're able to do. This is the level of complexity that are those that are in the practice exam. This is the level of complexity that you can expect to encounter. Let's see. I wanted to turn on the chat so that I can see. Forgot to do that. All right, so it turns out that when I prepared practice exam 4, this is actually the first semester I've actually given out a formal practice exam for. In previous semesters, oh great, the Apple Pencil battery's slow. In previous semesters, I just told students, well, just go do some practice problems at the end of the chapter. In this case, I decided, since I worried that you guys would worry about that, I wrote my own practice exam, but in the process of doing that, some copy and paste things made it so that there wasn't enough information on some of the problems. So we're actually going to do some of those examples in class, and hopefully this will ease some of the anxiety. I don't know which problem on the practice exam this is. These are just slides which I pasted into that practice exam, so I don't have a number to give you. Someone on the chat is asking to discuss the final exam. Certainly. What's covered? Everything. What's the structure? Multiple choice. Number of questions, somewhere between 25 and 30. Time limit. If I do 30 questions, I'll give you 3.5 hours. And if you feel like, again, those with formal accommodations, I'm happy to build that in automatically. If you are a slow test taker and find yourself flirting with the 3-hour deadline on a 25-question exam and feel like you could use more, I'm happy to do that. I want to limit the time on the exam for a couple of reasons. First, it just helps everybody be more honest, because if you only have 3 hours, you're not going to waste time posting on some internet, Reddit or something like that. Don't trust the OChem folks at Reddit, I guess, but posting for help, because sometimes in our moments of panic, we become weak. It also makes it so that you have an incentive to just sort of face the music and move on with your life. I've discovered that if I have a time limitless exam, some students will spend 8 to 10 hours on it, and I really don't want to affect your life in that way. So this sort of allows you to spend enough time on it, make a decision, and then move on. Again, if your situation is such that that is a problem for you, you're welcome to email me and we can see about coming to an arrangement. What's on the exam? I said everything, so everything from exams 1, 2, and 3, and then this last section, how much of which and what, I have no idea. So what are you going to do in the next little bit before the exam starts? Make sure you know how to do this last stuff, work on practice exam 4, and then focus on reviewing the stuff that you know you are weak on. And that's where you will stand to gain the greatest possibility of maximizing your score on the exam. If I ask a question about something that you know how to do and it's easy for you, then great, you lucked out. If I ask a question about something that's hard for you and you worked on it and fixed it, then yay, you're not vulnerable to that anymore. If you didn't fix something and I don't ask a question about it, then also you lucked out. But then if you didn't fix it and I ask a question about it, then you're leaving points on the table. And my guess is that none of you are especially concerned or especially anxious to leave points on the table. I did not say what percent was on past stuff. I could make up a number, but it would not end up being accurate. So, all right. So let's practice NMR. Hopefully we've got enough charge on the Apple Pencil to work for a little bit. This is one of the problems that I think, as presented in your practice exam, was just the spectrum and not the data. So it would have been hard to solve without that information. You're given a reaction, and or at least two different starting materials. You're given a product L, and you're shown that its M over Z ratio is 90. That means its molecular weight is 90. Now, we could start this problem in a couple of ways. We could try to figure out what molecular formulas would be consistent with 90 molecular weight. And that might work, though it's convoluted, and I haven't really taught you how to do that, though there's information in the text as to how to do that. Or we could start with the spectrum and then see whether our answers that we're coming up with agree with the final molecular weight. At least we know what some of the starting material pieces are. Let's review what we know from the NMR spectrum. Starting at around 5 or 4.5 ppm, we have a peak that is a quartet, which we've interpreted before as meaning it is adjacent to 3 protons. We have at about 3.3 ppm a singlet, which means it's adjacent to no protons. And then at sort of 1 point, whatever it is, 1.4, you have a doublet, which would mean that it's adjacent to 1 proton. Already, I would suspect that the proton represented by the 1.4 ppm peak is coupled with the proton represented by the 4.5 ppm peak. And though, because those are the only two peaks that are split, and so they'd have to be coupled with each other. Now let's deal with peak area, all right? This is kind of challenging in the sense that they didn't give you, oh, this is 1 proton, this is 2, this is 3. They just gave you these numbers in arbitrary peak units. So we're going to have to make a judgment call. So as I said, you can add up all the integrated peak areas and then divide them by the number of protons that are in the molecule, but we don't really know that yet because we just have a molecular weight and not a formula. Alternatively, you can look for reasonable ratios. So we can start by taking the smallest peak, which is this one that integrates for 7 arbitrary peak units. And let's just pretend that that is equal to 1 proton. Let's just say, for now, this is trial and error, so we can erase whatever we don't like. Let's tentatively say 1 proton. If that's true, then how many protons would be represented by the rest of these peaks? Well, 46 is somewhere between 42 and 49. So this could be somewhere between 6 and 7 protons. So let's just say 6 or 7. Now, actually, I can rule one of those two out just with logic. I've got a singlet here, meaning 6 or 7 protons are identical. Now, it's very difficult for me to think of a way that I could have 7 identical protons. It's possible, but it's only in rare situations. Much more possible and more reasonable would be to have 6 protons identical to each other. That would just be 2 identical CH3 groups. So I'm going to go with 6 as my tentative judgment call. Now I can always come back and say, well, maybe it was 7. But yeah, now I and somebody mentioned in office hours, well, yes, if you divide 46 by 7, it's closer to 49. So isn't it a better judgment to say it's 7? Fine, but it doesn't work. So you can do the math, but you also have to use a little bit of chemical common sense and this decision between, okay, how am I going to get 6 protons identical to each other? The only way to do that is for them to be 2 identical CH3 groups. Or I suppose 3 identical CH2 groups, whatever. But we're settling on 6. Okay. The next one, 25 divided by 7. 25 is right in the middle between 21 and 28. So again, you're going to have to make a judgment call. It looks like it could be 3 or 4 protons. And so we can choose either possibility. It's easier to get 3 identical protons than it is to get 4. So I'm going to, again, sort of stick with 3, and I can always come back and revise that. All right. So let's start to build up some structures based on what we know. 1 proton adjacent to 3. So that could be something like this. No? Yes? Yeah. These are 1, 2, 3 bonds apart. So if I had some structure like this, I would expect this proton to be a quartet and these methyl group protons to be a doublet. And so far, that's consistent with the data. In fact, we can label these peaks A, B, and C, and I feel pretty good at assigning the proton in this structure to A and then the methyl group here to C. So I know whatever this molecule is, it probably has that structure. And in terms of what I was told about the chemistry, it looks like they come from there. All right? Now, I've got some chemical shift information that I can use. I've got 6 identical protons, and they're at 3 ppm. I've got 1 proton at 4 ppm. Those are both in the range of being adjacent to an electronegative atom. All right? So, and I know there's some oxygens involved based on the starting material. So let's just say, what if I put a CH3 group here on this oxygen? Then this proton A would be adjacent to an oxygen. So you'd expect its ppm to be low, expect its chemical shift rather to be de-shielded and high. And then this methyl group would also be a singlet because it's not adjacent to any protons. Okay, but I have 6 protons that I need to explain with this singlet peak. So what if I do that? What's wrong with that? It's not a singlet because it's adjacent to A. In fact, if we did this, then this would be identical. This methyl group would be identical to proton C. They would both be a doublet. This would integrate for 6 protons, and it doesn't. Okay, so what am I going to do? Well, what if evidence suggests that this methyl group is a singlet and de-shielded? Being bonded to an oxygen is a great way to do that. And if there are 2 methyl groups that are identical, the only way to build that in this situation would be to have 2 of those methoxy groups there. All right. Let's see if what we have agrees with the data. Singlet methyl group, identical to each other and at a chemical shift that's de-shielded, check. Quartet, single proton, and it should be de-shielded because it's adjacent to 2 oxygens. And in fact, it actually makes sense that this proton shows up even more deshielded than the methyl group does. Each methyl group is adjacent to one oxygen. This proton is adjacent to two. So that makes sense. And then at last, methyl group C, adjacent to just one proton, should be a doublet. And shouldn't be very deshielded because it's farther away from the oxygens. So now we can actually, now that we've got a hypothesis, we can check and see, does it agree with this molecular weight? And so counting the carbons, 1, 2, 3, 4. So C4, H, let's see, 3, 6, 9, 10. And then 2 oxygens. And you can do the math to show that that's actually right on for the molecular weight. How is A a quartet when not bonded to a CH3? A is adjacent to 1, 2, 3 bonds away from the methyl protons. All right, good. What else? Other questions? Yeah.
When you were solving it, you did use like the aldehyde, the other information that they gave you, right?
Yeah. So I could have used this. Actually, in 352, you will learn a reaction that makes this very clear. But even without that, what looks like happened is you added 2 methyl groups, you got molecule L, and in order to make it all balanced, you would have had to lose water. Just as a preview, this happens to be a functional group that's called an acetal, and you should get to that in chapter 20 or 21 of 352. Yeah?
Sorry, why do we have 2 B's?
These 2 methyl groups are identical to each other, so they're both represented by this 6 proton peak. Yeah. Why is proton A even more deshielded? Because proton A is adjacent to 2 oxygens, right? This oxygen here and this oxygen there. If you were adjacent to just 1 oxygen, you show up in 3 to 4. If you're adjacent to 2, you can be even more deshielded than that. There are tools for sort of predicting this based on adding together the effect of 2 oxygens. We don't need to go there. Being quantitative is not that useful in this case. Just recognizing that because that proton is adjacent to 2 oxygens, it can be even more deshielded. And that's all you need to know. If there is an OH group or a carbon-oxygen double bond, I will definitely give you the IR data. I believe I'm not willing to commit to that. I will say that there will be enough information in each problem that you can solve it, and that you'll have more than enough information to solve it. All right. What else? Yeah.
So just to go along with that, what other structures would we need IR data for other than a carbonyl or an hydroxy group?
What other structures would you need IR data for? The ones that I've told you about, the carbonyl and the OH group, are enough.
That's it?
Yeah. Okay. Another one that was sort of botched in the practice exam is this one, because I didn't give you this formula or this equation or the molecular formula. So I thought, if it's okay, we would work here. Sorry, Emma, you're asking about problem L. Are there too many carbons? 1, 2, 3, 4. Let's see, if I add 4 times 12 is 36, plus 10 plus 2 times 16, which is 18. 1, 2, 3, 4, 5, 6.
2 times 16 is 32.
Yeah, yeah, thank you. I'm very sorry.
12 is 48.
Joshua Price. You're witnessing here. You are all witnesses to my inability to do arithmetic fast in my head. You got the 10 right. That was easy. Okay. 4 times 12 equals, carry the 1, 48. 10 times 1 equals 10. 2 times 16 equals 18. Oh boy, 590. We have correct molecular weight. Thank you. Sorry about that. And if you want to test me on right hand versus left hand, I will get that wrong more than 50% of the time. You're on my right side. See, I did it again. That was on purpose, but okay. So question, whatever it is, problem M. The way I would start this is use the information in the molecular formula to tell you whether you need any double bonds. And if you did that, you would discover that there is one pi bond or ring, one double bond equivalent, or 1 degree of unsaturation in this molecule. Now that starts to make sense in light of what you're given for the chemistry here. Those are dehydration conditions from chapter 9. Toluene sulfonic acid is a strong acid. You would first protonate the OH group to turn it into a good leaving group. You would presumably make this carbocation intermediate, and then you could do the elimination chemistry. So actually, rather than try to solve the problem starting with the NMR data, we can actually generate some hypotheses for what the structure should be and then compare those with what the NMR data are telling us. So there's your carbocation. I look for beta protons, 2 different kinds of beta protons. I also look for carbocation rearrangement. And where I've been trained to look for carbocation rearrangement is where I have a secondary carbocation next to a tertiary or quaternary carbon. And it looks like I'm in that situation here. So I might be concerned that this carbocation would rearrange via a 1,2 hydride shift to give me that product, right? So let's consider the kinds of products we can expect. If we remove this beta proton, we would have that product. If we remove this one, we would have potentially this product, cis and or trans isomers, but maybe the trans. We can write the cis one as well. And then if we remove this beta proton, we would get the blue product again. Whereas if we removed a beta proton on one of the methyl groups, we would get that product. That's looking vaguely familiar from chapter 10. If it's not, that's something you can go back and review. So now I'm told there are 2 possible products, M and N. So these are actual data. This is a case where I don't actually observe some of the possibilities. So I want to find out which of those possibilities I observe. All right, let's start to look at what the data tell us. I have 1 proton at around 5.1 ppm. That is consistent with the chemical shift expected for a vinyl proton, and you would see that looking at a chemical shift table. In terms of splitting, it looks like a triplet. So here I would be maybe proposing a structure where I have a hydrogen on a vinyl carbon, and what's here is a CH2 group. I don't know what the rest of the molecule is going to be, but so far it looks like I have this structure. And the other thing I know is whatever is here, there are going to be no protons on that vinyl carbon. Because if there were, they should be splitting this, and they should show up as another peak in the olefin region. Okay, everybody, go ahead.
Is the peak at 7.3 or something like that account for anything? Or
Sorry, does the peak at
7.3?
There's a peak at 7.3. What the heck is that? They didn't integrate it for you, meaning that it probably is small enough that it doesn't belong to this molecule. It may be an impurity. In fact, what this likely is a solvent peak. I didn't teach you guys this. You'll learn it in 353. But of course, we put all of these molecules in solvent to do the NMR experiment. The solvent can't have any protons in it because otherwise they would overwhelm the signal. So we choose a solvent where all of the protons have been replaced with deuterium. One of these is deuterated chloroform, CdCl3. However, CdCl3 is slightly acidic, and if you leave it open to air, a little bit of it becomes CHCl3. So what you're seeing there is residual CHCl3, and that will often show up in a real spectrum when you're using deuterated chloroform. So you just learn to ignore that. Other questions so far? Okay, let's keep moving down the spectrum to lower chemical shift and see what else we find. Here we see a 2-proton pattern with lots of lines in it. It is at around 2 ppm. They haven't zoomed in on it, by which we can conclude they don't necessarily want us to interpret it. So next to more than 3 protons is probably what we can conclude there. Now, as a matter of fact, if you look, it looks like this is a quintet, 5-line pattern, and we can interpret that, but it's not necessary for solving the structure. Here at around 2.3 ppm, I see a 3-proton singlet. So whatever this is, it's adjacent to 0 protons. I see another 3-proton singlet, meaning this is also adjacent to 0 protons. And the fact that these two show up differently says that the methyl groups are non-identical. So I'm going to have 2 non-identical methyl groups, each not next to protons. Then finally, I see, lastly at this chemical shift, I see a 3-proton triplet, suggesting this is a CH3 group adjacent to 2 protons. Okay. Looked at all the peaks. Now I can start to ask which of these is most consistent with the data. So let's look at what we would expect for these orange products. How about these 2 methyl groups? How many, in our orange product, how many protons are those methyl groups adjacent to? 1. So each of those methyl groups should be what kind of peak?
Doublet.
Should be a doublet, right? We would expect that methyl group to be a doublet. I'll indicate that with a letter D. By the way, are those 2 methyl groups the same or different?
Same.
They'd be the same, not different. Do I see a doublet integrating for 6 protons? Nope. Go ahead.
we know that those are two singlets, but if it didn't have each of them having 3 hydrogens and just have one bracket saying it's 6 hydrogens, would this mean a doublet?
Could you have assumed that that structure was a doublet? You would have had to be careful there. You would have needed to measure this distance and see whether that's consistent with a typical coupling constant of 7 hertz or whether it's larger. Looking at it, my sense is that that's much larger than a coupling constant would be. Yeah. All right, others? So actually we can rule out the orange option, and there's another reason we can rule out the orange option too. Orange option has 2 alkyl or 2 vinyl protons, and we only see evidence for 1. So these 2 are not observed. All we've got to choose from then are blue product and red product. So let's see how we can distinguish these. In red product, we have 2 vinyl protons. We don't see evidence for 2 vinyl protons here, just 1. So whatever red is, it's probably not M. So probably M is our blue structure. Now let's go back and see whether we can reasonably conclude that, see whether our structure for M is consistent with the data. To do this, let's actually zoom in on M, and let's see whether we can assign individual protons in M to the peaks that we're observing. All right, protons here, methyl group A, B, vinyl proton C, CH2 group D, methyl group E. All right, starting with methyl group E in reverse alphabetical order. Because let's face it, end of alphabet names, didn't you hate being called on consistently last every single time in elementary school when they're going down the list of people? Always had to wait to be the line leader because you call on the A's and the B's first. Anyway, sorry. I guess I have some residual issues from elementary school. My last name is P. It isn't even that far along in the alphabet. Last names starting with P were very common in my junior high homeroom, and there were 2 or 3 other kids in that range named Josh as well. So I was just one of many JPs, which was kind of weird. Maybe that is why my friends called me JP Mormon, which I think was silly. And it was vaguely related to, we were learning about the robber barons in U.S. history, and we had learned about wealthy, I don't know, whoever, J.P. Morgan, and they decided that J.P. Mormon was hilarious. But now I would have to tell them, no, please, J.P. Latter-day Saint. Okay. So, yes, starting with letter E, we really got sidetracked there. You would expect for that's a methyl group adjacent to a CH2 group. So you're going to expect there a triplet. And because it's not next to any electronegative atoms, you're going to expect this to be relatively shielded, meaning low chemical shift. We got one of those. Proton D, well, this is next to a methyl group and a single proton on the next carbon. Next to 4 total protons, we're going to expect to have it integrate for 2 protons, but possibly be complicated. And we got one of those, that complicated 2 proton line. Now you can pattern. You can actually see a quintet there, which would be consistent with 4 adjacent protons where all of the coupling constants are similar. Proton C, a single vinyl proton adjacent to 2 other protons, looks like that. And then protons A and B. I don't know which one is A and which one is B, but they're both singlets. So we got it. That has to be our answer. Yeah? How are A and B chemically different? A is cis to the proton, B is trans to the proton. They are diastereotopic because they are in opposite positions on the double bond. Okay, Yeah.
Of those, which one would be A and which one would be B?
Yeah, which one would be A and which one would be B? I don't know.
Okay.
And I wouldn't ask you to do that. And you don't actually need to know that to solve the structure. What else? Yeah.
I guess I didn't recognize why the red structure is not M.
Why the red structure can't be M.
Yeah.
The reason for that is this is the NMR structure of M. In the red structure, you don't have three different methyl groups for one thing. You have one methyl group here and another methyl group there. In the NMR structure, we have 1, 2, 3 CH3 groups. The other thing that doesn't match is M has the red one has 2 vinyl protons. We only see 1.
Right.
Yeah. And then the splitting pattern also doesn't match. Did I see another hand that I missed? No? Yeah. All right. So now we got our hypothesis for what the other one is, the red one. Let's see whether that's consistent with the next structure. Why are A and B not adjacent to each other? Yeah, the methyl groups are, the issue is that the protons on A, protons A on that carbon, and the B protons are 1, 2, 3, 4 bonds apart. 4 bonds is generally too far to observe splitting. Splitting, we generally observe 3 bonds apart or less. Okay, so here's our hypothesis for N. Let's see whether this starts to agree. What we would expect, we expect to see a CH3 group, and we would expect it to be split a 3-proton peak, relatively shielded because it's not near any electronegative atoms. What about its splitting? What should we see for that methyl group? Triplet, because it is adjacent to 2 protons, right? All right, so we'll call this E. Wait, there may be, I don't know what to call it. We'll start with A. B, C, D, E, and F. All right, what do we expect for protons B? That should be a 2-proton peak. What should its splitting be? It's adjacent to 2 here, but 3 here. So that's 5. So if all the coupling constants were the same, you'd see a 6-line pattern, but it could be complicated. So we'll just say it's adjacent to 5 protons, could be complicated. Protons C, a 2-proton peak, what should its splitting be? Triplet, because just adjacent to 2 protons. How about the methyl group? 3 protons, what should its splitting be? Any protons within 3 bonds? Oh, it's you guys again. Dallin and his friend Mac. My office is indeed locked. How long you been sitting there?
For a second.
Okay. Okay. Last time Dallin raised his hand and I thought he was a class member. I'm like, oh, I haven't seen you here. Oh, it's you, Dallin. Okay. Are there any protons within 1, 2, 3 bonds? Nope. You got no adjacent protons, so we would predict a singlet. How about these two? Are they identical to each other? Not chemically, right? Because one is cis to the methyl group, the other's trans. In terms of chemical shift, they might be close. We don't know whether to expect them to have similar or different chemical shifts. They might couple with each other because they're different, but it could also be complicated. So we expect to see 2 vinyl protons. In terms of the splitting, we're not sure. They are so much more enthusiastic than you guys are. They're like, yeah, it's done. And you guys are like, we have a test coming up. Quit wasting time. All right, let's see what we observe. We have a triplet integrating for 3 protons. That's probably A. We have a singlet integrating for 3 protons. That's probably D. We have a complicated 2-proton pattern. That's probably B, which we said was going to be complicated. We have a 2-proton triplet, probably C. And then lastly, A, B, C, D, we have 2 vinyl protons. Not sure what we're seeing there. We could be seeing 2 singlets that don't couple with each other, or we could be seeing 2 overlapping doublets. It's really hard to interpret that, and you don't actually need to conclude that this is what the structure has to be. All right. Yes?
Do the overlapping doublets come from the fact that E would impact F and F?
Right, so if E and F are different, they can have a coupling constant between them. I don't know how big it would be. To see 2 overlapping doublets, you'd have to have a doublet here and a doublet there that's very close in chemical shift. And that's really hard to distinguish between just 2 peaks that don't couple with each other. To do that, we would need to measure this distance, and there would be some other experiments we could do to tell the 2 apart, but it's not necessary for this problem. Okay, so overall, our strategy is use all the information you have. The strategy is make sure that the structure you propose is consistent with the data. That's where many people get in trouble, is they'll panic and choose an answer that is consistent with some of the data, when upon further reflection after the exam is graded, they will see clearly, oh, I see now that my answer says that there should be a methyl group that's a doublet, and that's actually not what the data say. Why did I not see that? So I'm warning you, check your NMR answer, make sure it's consistent with the data. Okay, are there other problems from the practice exam you wish to see? Alternatively, let's see, here's a question from the chat. When a carbon is adjacent to multiple carbons with hydrogens, like B, when do you know if the coupling constant is close enough versus, okay, so let's deal with proton B. Your text actually, I believe, makes this more complicated than it needs to be for proton B. A lot of B's here. Your text says that you can see when you have a proton adjacent to multiple protons, you've either got the N plus M plus 1 rule or the M plus 1, M plus 1 multiplied by each other rule. An example of that is, say, proton A adjacent to B and C. If the coupling constant between A and B equals the coupling constant between A and C, then you use the N plus M plus 1 rule, which means you see a triplet in this case. If that criteria is not equal, your text says that the total number of lines you should see will be N plus 1 times M plus 1, which in this case, N equals 1, M equals 1 for the 2 adjacent protons. So you'd expect to see 4 lines. I've, without using that math, taught you that when the coupling constants are not equal, you can expect to see a doublet split into 2 additional doublets. That is called a doublet of doublets, a 4-line pattern. What I think Olivia is saying is for protons B, they're adjacent to a methyl group and to a CH2 group. So adjacent to a CH2 group, you would expect to see a 1 to 2 to 1 triplet. If the next coupling constant with the CH3 group is identical to that, you're going to see the same thing you would see as if you were adjacent to 5 equivalent protons. If not, you could see each of these individual peaks split into its own quartet. And the intensities of those quartets would each be 1 to 3 to 3 to 1, and then relative to each other, 1 to 2 to 1. And so that's a 12-line pattern. But it could be something even messier than that. I don't find that useful, and I'm not going to ask you to interpret anything that's more complicated in terms of this rule than a doublet of doublets. But this is why you can be aware that if you're adjacent to more than 3 protons, the pattern that you see could be complicated. It might be simple if the coupling constants are all equal. If you zoom in on problem 2, that looks like a 1, 2, 3, 4, 5, 6 line pattern. It looks like a sextet, which would mean by the n plus m plus 1 rule, a total of 5 adjacent protons, and that's consistent with what we see. But if the coupling constants were different, it might be more complicated than that, and I'm not going to ask you to interpret that. All right, other questions? Some folks ask occasionally, what do I do if I want more NMR practice problems? So let me see about, let's see, NMR. Who knows what Dallin was looking up on YouTube? Nmr Practice Problems. And I found a few resources this morning that are kind of interesting. The top 2 results are actually decent. If you go to this one, it's from UCLA, and it's from several years back. But you can click on any of these beginning problems, and it will show you what the formula is. It'll show you the C13 spectrum too, though we've not talked about that, and I'll leave that for your future 353 experience. But if you click on the proton spectrum, it'll show you this spectrum for the molecule, and then if you it will show you peak integration lines in red. You can just judge by their relative heights what the ratios will be. This is sort of just loosey-goosey, back of the envelope. Looks like 2 to 3 to 3 to me. You can click on an individual peak and it will zoom to it, and you can see, okay, that's a quartet, that's a singlet, that's a triplet. You can use that information, and then once you've figured all of that, you can look at what the solution is. So that's one place with a lot of different resources. The format, it looks different than you may be used to looking at, but it is a source for other practice problems. Another one that might be useful to you is the next one on the list from Google. When you Google Nmr Practice Problems, these are both old websites. I think they maybe haven't been updated since the early 2000s. But you can click on any of these spectra, and it will show you a spectrum. This isn't that useful. There's just one peak. Let's click on another. It'll show you the spectrum. Over here, it will have told you what the peaks are and what their areas are, and then you can click on each individual peak, and it will show you what kind of doublet it is, or a singlet, or so on. And then you can click on the solution to see what the molecule is. So if you need more practice or you want to test yourself, that's one place you can go. Peak area just represents the area underneath the peak, which is proportional to the number of protons represented by the peak. So with that, good luck, and I will make the test available to you starting Friday.